In this screencast, I'm going to discuss parametrizing surfaces. We're not going to do much with this, but I wanted to give a little discussion. And let me just recall the situation for curves in R3. So if we wanted to do some calculations on a curve, we work with the parameterization RT. That's how we do our calculations. And it might be sometimes the case that one is told a curve, one is given some specification for a curve. Here I'm sketching a parabola, and you're not told the parameterization. And the very first thing you have to do before you can do any calculation is to produce a parameterization for that curve. Right, a similar situation holds for surfaces. It might be the case that you're given that you're told some surface that you're to compute some surface integral or some normal vector for, say. Here I'm drawing a cylinder. That's not a very good one. And you're just told the geometric object. And so the very first thing you would have to do is produce a parameterization R of two parameters, in general called U and V. Right? And just to be clear, that means providing x of U and V, y of U and V, and z of U and V. Of course, your parameters might not be called U and V, but that's the idea. You should certainly be able to parameterize simple surfaces like pieces of cylinders and pieces of spheres. With that in mind, I have some example problems here. And the first is find the parametric representation of the part of the sphere, so this sphere given by this equation, that lies between the planes z is equal to -2 and z is equal to +2. Alright, so let's have a little sketch here. So the first thing you should realize is that the sphere has radius 4, so radius 4. So let me draw a sphere. I don't think I need the coordinate plane, so I don't think I'll draw them. So this is meant to be a sphere of radius 4. Well, actually, maybe I do need the planes. All right, so this is what we're concerned with, z in particular. So this here will be +4. This will be -4 because the sphere has radius 4. And just to say that plus and -2 is clear within this interval. I think you can see what it's going to look like. I'm going to cut this part way here. And I'm just going to go ahead and cut off this top piece. Right, so that's not part of the sphere that we're going to consider. And likewise, you're going to cut it here at z is equal to -2. Let's get something attached. So I'm going to cut off this piece. All right, so that's the surface that I'm going to consider. And the question is, how do you parameterize that? Well, there are various approaches. I would just do what's probably the obvious thing, which is to do this in spherical coordinates. And since the points lie on a sphere, in fact, we can just go right for this R of, again, I'm just going to use the usual. I'm not going to call them U and V. I'm going to call them theta and phi because I can keep that straight. So if this were just a full sphere, what would we have? Well, x is a sphere of radius 4, so I'd have x is equal to 4 sine phi cosine theta, 4 sine phi sine theta, and 4 cosine phi. Okay, so that would be the parameterization of the full sphere of radius 4. And now let's just have a look here. The theta coordinate is not restricted in any way. It's going to run from 0 to 2 pi, just as for the full sphere. So this parameter theta will be from 0 to 2 pi. And then the only restriction will be on this polar angle, or the colatitude phi. So that's going to be restricted, and that's what we have to work out. What are its bounds? Let's just do it algebraically. Well, we can see it right from here. So 4 cosine phi, that's the value of z in spherical coordinates, that has got to be equal to plus or minus 2. That will determine the values of phi that correspond to these values of z. Is that clear? So z is plus or minus 2, plus or minus 2. We want to know what values of phi they correspond to. That is to say, phi will be equal to pi on, don't have quite enough room here, pi on 3, or 2 pi on 3. And so, just to be completely clear, I'll do these in yellow. You know that there are these cones here for phi is equal to a constant. And, all right, so this z value is +2. This z value is -2. And the corresponding angles are, that angle is pi on 3. And then this angle is 2 pi on 3. So that's all you have to do then. And that then is your parameterization of this surface. All right, so again, it's just a subset of the sphere of radius 4. So again, that's the kind of thing you should be able to do if parameterize, say, the upper hemisphere or the lower hemisphere or something like this, because it just amounts to restricting these the angles in the standard spherical coordinate representation of a sphere. Enough about that. Let's go on to the next one, which is actually even easier. Find the parametric representation of the part of the cylinder, x squared plus y squared is equal to 4, that lies to the right of the xy plane. So again, I'm going to draw it. I guess I'll draw the coordinate axes first. So let's draw. Okay, that is meant to be a full cylinder. Of course, it goes. Let me just say, it goes off to plus or minus infinity. There's no restriction on z here. You'll see here, hopefully, that corresponds to radius equal to 2. So let's, in fact, in particular, let's label this as that corresponds to x equal plus 2, and this there's a point back here in the back, say, corresponding to x is equal to minus 2. Now, we only want to consider part of this cylinder. We want to consider that is to the right of the xy plane, except that should be xz plane. So I'll change it now. That is to say, there's a plane here. I think I'll do it in yellow, in fact. This is the xz plane. And I only want to consider part of the cylinder that lies to the right of it. That is to say, in this direction. Again, that would have to be clear to you what to the right meant, but this is what I mean in this case. So in other words, I want to cut off all the back part of this cylinder. Cut this all off here. So there's a line there. Okay, do you see it? All right. Again, I'm taking a little time here because I want you to get used to drawing. All right, so that's what it is you have to parameterize. Now there are two ways to do this. So what I would have done, just sort of almost without thinking, is I would have just used polar coordinates, and so I would have, cylindrical coordinates, said, all right, so this is obviously a problem in cylindrical coordinates. The radius here is fixed at 2. So I would have said, I would have used theta and z, and fixed the radius at 2, so that x would be equal to 2 cosine theta, y is equal to 2 sine theta, z is simply equal to z. All right, now z is clearly unbounded here because I haven't restricted it in any way. So in fact, I'll just say z is any real. Z is any real. This corresponds to theta equals 0, and that corresponds to theta equal pi. So rather than theta going from 0 to 2 pi, theta goes from 0 to pi. Okay, so it's that simple. So that's a parametric representation of this cylinder. But there is a different approach, which I guess could come up at various times, is you could view this as a graph. So you can view that y now is a function of x. For any given x between -2 and 2, you have y. That is to say, think of y as, let's just do it this way, y is equal to some h of potentially x and z. Now it only depends on x. It'll be equal to the square root of 4 minus x squared. Okay, because z is always positive. This is the way you can do it. In which case, I could have my my parameterization r of, and just for different, let's just call them u and b this time. I'll just take u to be the x, then y will be equal to 4 minus u squared, and then v will be z. That is to say, this will be z. And what are the restrictions? So what are the parameter ranges here? Well, again, v is z, so that will be any real number. And u will go between -2 and 2. All right, so this would be another parameterization of the same cylinder. And for some purposes, this might be better. Although in general, I think that this more naturally captures the relevant symmetry of the problem. So in most cases, that will be better. All right, so that's two examples. As I said, you should be able to parameterize pieces of cylinders and pieces of spheres, and perhaps other very nearly trivial geometries.